Welcome back. In the last few sections, we've been going through the process of manually fitting different models and deciding which one fits the data best. In this section, we will learn how to leverage Python to do this instead of us. Right. Before we get coding, let's spend a minute to discuss how the method we'll be using works. It's called ARIMA, and as you can guess, automates the ARIMA model selection. For starters, it takes the data and fits many models with different orders before comparing their characteristics. We can decide whether Python should do the fitting simultaneously or one by one. The choice is simply up to you and the processing power of your machine. The simple example we are going to show you won't require huge amounts of time to compute. Therefore, you could use whichever one you prefer. However, the processing time increases substantially when we try out more complex models. So have in mind that it might take Python a few minutes to compute. So, we know this method fits different models, but how does it determine which one is the best? Earlier, we discussed how the correct model should yield the highest log likelihood and require the lowest information criteria. So how would this method ensure the best model excels in both measurements simultaneously? Well, it doesn't. This might come as a shock to you, so allow us to elaborate. Information criteria like the AIC and BIC depend on the log likelihood. To be more precise, the formulas for both these metrics use the log likelihood value of the model. Hence, if the method adapts the AIC as the sole criterion it uses to measure the goodness of fit, this would indirectly imply that the log likelihood is high. Therefore, this method cycles through models with varying orders and specifications, and out of those, returns the one with the lowest AIC. That's what we've basically done so far. Now, AIC is not the only criterion. Another good choice is the BIC, but we'll talk more about that when we start coding. Okay, there's one last topic we need to discuss before we can get some hands-on experience. The pros and the cons of using this approach. On the plus side, this method can save us an enormous amount of time and eliminate the need to understand the statistics and theory behind model selection. It also removes ambiguity around the best model and makes the LLR test redundant, since we don't have to compare models against each other. Using this method will also reduce the risk of human error and the possible mistakes caused by an incorrect interpretation of the results. As for the negative side, there are several drawbacks to using this method. The first one is that we're blindly putting our faith into one criterion. Even though the AIC incorporates the log likelihood value, we should still be cautious. What is more, we never really see how well the other models perform in comparison. We'll never know whether any of them were close to the one method recognized as best. Moreover, from my experience, depending on the context, the definition of best varies a lot. It may be the case that a simple AR2 gives us almost as good results as SARIMAX 201-1025, while the ARIMA would choose the more complicated model. In real life, if the results are comparable, we may opt for the much simpler one, even though it provides worse results. Lastly, improper use and incorrect argument values open a different channel for human error. If we misinterpret the default values, we might be thinking we're examining one type of model, while in fact, a completely different one is being fitted. A recent example of this is the default value for the volatility argument of the arch model method. While it makes sense for it to be set for fitting an arch model, the default is actually set to garch instead. Similarly, if we mistype the name of an argument, the method does not return an error, but simply ignores it. This could mean that a small lapse of concentration can lead to wasting tons of time fitting models which are not interested in. Of course, the last drawback is more of a warning and is entirely in your control. Thus, please pay attention when using the ARIMA. Alright, now that we've explained how the method works, we're ready to set up the code. In the next lecture, we're going to set up the environment before using the model. Thanks for watching. Hello again. Picking up where we left off, it's time to set up Python Notebook for this section. As discussed, we will employ the ARIMA function provided by the Pyramid ARIMA module. Since this is a package we haven't used before, we need to pip install it. In case you need a refresher, you can go back to the lecture titled Installing the Necessary Packages at the beginning of the course. Okay, it's time to import the module. For your convenience, we've provided you with a template notebook file, which already contains the necessary code for importing and pre-processing the data. We recommend opening this file now, as doing so would make your work much easier. Unlike the pre-processing parts of some templates so far, we've compiled the returns for all 4 indices before splitting the data. We're also not removing any of the columns. This will make it easier to use the code for practice and the exercises and implement the max models. Right. Time to import AutoARIMA. We simply type from Pyramid ARIMA, import AutoARIMA, and we're pretty much done. In our next lecture, we will fit our first AutoARIMA model. Thanks for watching. Hello there. Last time we set up everything we need, so now we can see how AutoARIMA works. As usual, we start by selecting an appropriate name for the variable storing the model characteristics. In this case, we can't use the elaborate naming system we set up earlier because we don't know the appropriate orders. Having that in mind, let's go for a more universal name, like model auto, and set it equal to the AutoARIMA function. Next up, we need to state which time series we are modeling. Since we've been using footsie returns so far, let's go with that. Just make sure you skip the first period, since there's no data available for it. Okay, let's run the code without setting values for any of the optional arguments. That way, we can see what the default best ARIMA model will be according to the package. Note that these defaults aren't always optimal or reasonable, and we will discuss them at length in the upcoming lectures. Next up, we can just call the model auto variable and examine the characteristics of the best fit. From the arguments I see, I can tell you that we are dealing with an ARIMA 4.5 model. But let's display a summary table as we usually do and see why exactly it is an ARIMA 4.5 model. All right, the table clearly states a SARIMAX 405. What's going on here? First, it's worth mentioning that the SARIMAX is the most general model. It includes seasonality, auto-regression, integration, moving average, and exogenous factors. So AutoARIMA takes a SARIMAX model as the backbone. And if there's no autoregressive order, for instance, it would simply set it to 0. Okay, let's examine the SARIMAX up close. There are 3 very important features. For starters, we know that a seasonal model contains 4 more orders than a non-seasonal one. Not seeing them here suggests that this is a model without seasonal components. Of course, this is backed up by the model arguments we examined in the last video, since they stated a seasonal order of 0, 0, 0, 1. Thus, at most, our model could be ARIMAX rather than SARIMAX. Next, since the order of integration D is 0, this is a non-integrated model. Therefore, we're not even using an ARIMAX, but an RMAX at most. Additionally, we didn't set an exogenous variable before fitting. We also didn't see one estimated among the coefficients, so it's safe to assume this is not a max model. Therefore, the most complex this model can be is an ordinary ARIMA. The autoregressive order is 4, while the moving average one, 5. As you can see, even though it isn't clear at the very beginning, this is an ARIMA 4.5. Okay, you can add this complex interpretation to the cons of using AutoARIMA. Moving on from the model part of the table, we want to draw your attention to these sample values. It says the sample goes from 0 up to 5,020. If you recall, our training set contained 5,021 elements, so this simply states we're using all of it to get this model. The name sample comes from the in versus out of sample split we make when we want to validate a model. AutoARIMA has the functionality of taking the complete data set, automatically splitting it up, and then validating the model choice before returning a result. We'll learn how to do this in the following lectures. The rest of this table is self-explanatory and contains coefficients and their characteristics, as well as some test statistics you should be familiar with from prior models. All right. Before we discuss the full capabilities of the AutoARIMA method in the next lecture, we want to make a few quick comments on the results we got. The ARIMA 4.5 wasn't our preferred model of choice when we conducted our initial manual analysis. We disregarded it because some of its coefficients were not significant, as we can clearly see here as well. Of course, we explained that the rules of model selection are rather rules of thumb than fixed, so we can attribute some of the mismatch to different standards of model selection. Additionally, the AutoARIMA only considers a single feature, the AIC. The lower the AIC, the better the fit, regardless of the significance of some coefficients. This can be perceived as a flaw of the method. However, empirical research has sometimes shown that omitting certain lags can be beneficial to model estimation when clustering is apparent. Apart from that, we haven't discussed model testing and validation yet. Therefore, without realizing, we could have easily overfitted while going through the models in our previous sections. This is why we should be open-minded about the results of the method. However, there is another factor at play here. The default arguments of the method restrict the number of AR and MA components we are willing to include. In other words, we might simply be excluding the models we considered best in previous sections from the comparison. To make sure the AutoARIMA model tests exactly what we're interested in, we're going to familiarize ourselves with most of its arguments. In the next lecture, we'll discuss their default values and how and when to alter them to suit our preferences. Thanks for watching. Hello there. In the last lecture, we discussed the results of the default best model. In this one, we're going to loosen some of the restrictions and show you how to use the AutoARIMA method to the fullest. Without further delay, let's get coding. First, you can find a link for all possible arguments of the AutoARIMA as an external resource accompanying this lecture. You can pause the video now and familiarize yourself with it, or carry on with the lecture and examine it later on. We've summarized some of the most important ones in the template file we've given you. These are there to help you keep up as we go through the various arguments of this method. You can always refer back to them when using AutoARIMA, since the source file's documentation can sometimes look intimidating. Right. Let's start by setting our model variable equal to AutoARIMA. For the sake of consistency, we'll use footsie returns as the endogenous variable. In case you need a reminder, the endogenous variable is the one we are estimating. Of course, make sure to skip the first period since the data is not available. After setting the endogenous variable, it's only natural to add the exogenous one as well. We do this by passing a value to the exogenous argument. You need to be careful here because the equivalent argument for the ARIMA and ARIMA functions we've used so far had a different name, exog. If you enter the name of the argument incorrectly, the AutoARIMA method will automatically ignore it without showing an error message, so use with caution. So, we set this exogenous argument equal to the S&P returns. Do you remember how we computed the returns for all the indexes at the beginning of the section? Well, this is exactly why we did it, and why we didn't get rid of the other time series as well. We can use them as exogenous variables in our analysis. Now, here is a small bit of advice on max models. Make sure you're using the same type of data. Simply put, if your endogenous variable contains returns, then your exogenous one should as well. Analogously, if the former contains prices, then so should the latter, since mixing stationary and non-stationary data could lead to some misleading results. Of course, provided you have the data available, you can have multiple exogenous variables, so you can include the returns for DAX and Nikkei as well. Since they're all part of the same data frame, the easiest way to do this is by using double squared brackets and listing the names of the three attributes in quotation marks. That way the indicator, in the end, will automatically ignore the first values for all of these series. Fantastic. Now, if we believe there is seasonality in the data, we should indicate it. But how can we do that? Well, if we set specific seasonal orders like we're used to, it defeats the purpose of the auto ARIMA. So instead, we only specify the length of the season, which we denoted as an S in the Saramax lecture earlier. However, its corresponding argument in the method is called M, and you've probably figured out that the name comes from margin, since it tells Python the distance between seasonal observations. As you've already seen, we need to know this value prior to analyzing the model. To elaborate, the length of the cycle is determined by the frequency rather than anything else. Since we're using business days, there are 5 business days each week, we set M equal to 5. Great. So far, we've loosened up the restrictions of the default best fit by taking care of the seasonal and exogenous aspects of the Saramax model. What's left is expanding the ARIMA limitations, and the next set of arguments is going to do just that. The first one is called max order, and as you can probably guess, it determines the total number of non-seasonal AR and MA components the model can have. In other words, this is the maximum value for the sum of P and Q. We can either set it equal to some value we believe is sufficient, like 10, or set it equal to none. Doing the latter makes the auto ARIMA more flexible, since it can try any combination of values, which match the individual restrictions for the AR and MA orders. Note that this may increase the computational time significantly. Speaking of which, the argument max P sets the highest non-seasonal AR order a model can take. Since the default value is 5, and we were manually examining models with orders higher than that, we can set max P equal to 7. Identically, we can set max Q equal to 7 for that very same reason. By setting individual limits on P and Q rather than their total, we're ensuring the auto ARIMA cycles through all models with non-seasonal orders between 0, 0 and 7, 7. Okay. If we also wish to define a limit for the levels of integration, we must pass a value to the maxD argument. Usually 1 or 2 integrations are enough to reach stationarity, so setting it equal to 2 should suffice. All right. As you know, seasonal models require seasonal orders, which we denote with the uppercase letters P, Q, and D. Just like their non-seasonal counterparts, we can expand their restrictions too. You've probably already guessed it, but the names of these arguments are max P, max Q, and max D. By default, the first 2 are limited to 2, with the third one to 1. So we can loosen them up a bit by setting them to 4, 4, 2, respectively. Okay. Thus far, we've seen how to expand the types of different models the auto ARIMA can fit and compare. Now we can shift our attention towards arguments that are true for every individual model we're fitting. Sometimes, complex models that use many exogenous variables and/or have a high total order fail to converge. In layman's terms, the way these numerous factors affect the current period endogenous variable is so intricate that the regression fails to find the correct solution after a fixed number of attempts. We can amend this by increasing the number of times Python tries to find the correct solution. The argument is called max iterations, and its default is 50. For this particular model, 50 iterations should suffice, but we wanted to make sure you know how to increase it if necessary. Next up, we have alpha, which indicates the level of significance. We set it equal to 0.05, since we're constantly using a 5% significance level in our analysis. Because 5% is so commonly used, it's also the default value. However, we're defining it here so that you can easily adjust the code if we decide to rely on 10 or 1 significance levels instead. So far, so good. The next argument we want to examine is called njobs, and it's something we haven't used before. Since auto ARIMA has to go through numerous models before returning the best one, njobs tells Python how many models it should try and fit simultaneously. Technically, it indicates how many CPU cores should be utilized. We can set it equal to 2, 3, or even a big number like 10, but we're not doing any of that. Instead, we're setting it equal to -1. But wait, didn't we just say this represents how many models we're examining simultaneously? So how are we fitting a negative number of models? Well, we aren't. In some programming languages, including Python, negative indexes for certain methods or commands indicate that we're starting at the top and moving that exact number of values back. Since there is no such thing as -0, -1 means we're telling Python to fit as many models simultaneously as possible. This will make the iteration process a lot faster, depending on your CPU cores, of course. However, have in mind that doing this might end up slowing down your computer since we're operating at max capacity. Of course, the results would be the same either way, but since Auto ARIMA takes a lot of time, this may significantly increase your productivity. Okay, the next argument we'll be talking about is something you're probably familiar with already, and that is the trend. When using the LLR test, we'd sometimes have to specify that we'd assume either no trend or constant and a trend. To explain it briefly, we usually expect the endogenous variable to have some linear relationship with the values as well as a constant base factor. Therefore, we set trend equal to CT, which of course is short for constant and a trend. If you believe there is some quadratic relationship instead, make sure to change it to CTT. If you believe the underlying trend is more complex than that, you can use an array of Boolean values to express the pattern. For instance, the array 1, 0, 0, 1 would indicate a constant term as well as a trend of the third degree. However, this doesn't occur too often among price returns, so you need not worry about it. Just remember that the more trend factors we assume, the more coefficients our model is going to estimate. Right. Superb. This covers most of the basic arguments we can employ. In the next lecture, we'll discuss some of the more advanced ones. Thanks for watching. Welcome back. In this lecture, we'll discuss some of the more advanced Auto ARIMA arguments. Okay, so at the beginning of this section, we stated that Auto ARIMA only compares the models based on their AIC. However, that doesn't need to be the case. We can have a different information criterion as our preferred metric. The only factor that remains consistent is that we're relying on a single measurement to rank all the models. You probably figured this out already, but the default value for this argument is set to the AIC. Alternatively, we can change it to the corrected AIC, the BIC, the HQIC, or the out of bag. In the comments below, you can see what values we need to assign to the argument if we wish to use any of these alternative criteria. However, if we intend to use the out of bag or simply OOB, we need to separate the data into a sample and out of sample sets. We briefly mentioned this when discussing the results of the default best fit, but the Auto ARIMA has the built-in functionality to validate our model choice. Now we're finally ready to discuss how to use it appropriately. For starters, the argument we need to use has the very straightforward name out of sample size. The size part probably gives it away, but the values it takes must be numeric. For instance, since we have several thousand observations, we can set it equal to 1,000. That way, the method will automatically set aside the last 1,000 observations for validation and use the first several thousand as a training set. Usually, we want to make our code reusable, so setting a fixed value like 1,000 is not preferable. Instead, we can set aside a reasonable portion of the dataset. 20% is considered a good amount, so that is exactly what we're going to do. Therefore, we're going to use the len function to find the length of the dataset. Then, we will take 20% of that by multiplying by 0.2, since the two are equivalent. Lastly, just to be on the safe side, we can also call the int method and avoid the possibility of dealing with float values. Perfect. Before we run the cell, there's one last adjustment we need to make. Since we're letting the method validate the results, we no longer need to plug in the training set, but rather the complete data set. Therefore, we need to change the endogenous variable from df to dfcomp. Additionally, since the endogenous and exogenous variables should be the same size. We also changed the exogenous dataset to dfcomp2. The only thing left to do is run the code. Grab a coffee while the code goes through all the models we specified and examine the results in a few minutes. Of course, we won't make you wait, and we'll get straight to the summary table. We see that the new model contains fewer non-seasonal lags than its default counterpart. This makes sense, since we're allowing other factors to shift values between time periods. The current model contains exogenous variables as well as seasonal components, which make it extremely different from the original best fit. Additionally, the drift coefficient we're seeing here represents the linear trend coefficient. If you recall, we indicated that we expected to see a constant as well as linear term, and their coefficients are the intercept and the drift. On top of that, the AIC value has gone down from 15,000. This is a huge improvement in our preferred model, and we got it by simply loosening up the restrictions a bit. Wow, there you have it, an automated way to find the best fitting time series model. For homework, we encourage you to try out different values for some of the arguments of this method and discuss your results with other students in the Q&A section below the video. We've spent the last several sections talking about picking the correct model, but why did we need to know what this model looks like? We'll discuss this further in the next video. Thanks for watching. Hello again. Let's sum up what we've done so far. We went through plenty of models, such as the ARIMA, ARCH, and GARCH, and saw how they measure prices, returns, and volatility of returns. But what was the major goal of this whole exercise? Well, we did all of this so we could try and forecast these values into the future. One of these assumptions of time series is that patterns in the past persist in the future. This is why we try to model the past, in hopes of accurately predicting the future. Of course, this is no easy task, as we just witnessed. But finally, we're about to see if this was all worth it. The next step, after modeling the data, is forecasting it into the future. Exciting, right? I hope you're ready, because we'll explore how this is done in the next section of the course. Thanks for watching.